All right. I will have a study guide to you today for an exam that will take place a week from today. There is an assignment posted that will go over this pumping lemma that is due next week. The earlier you get it in, the more likely it is that it's turned around to you by the exam. That said, I'll have to do a little bit of logic on this because I don't think anything on that exam, on that assignment. Is there other things on that assignment that are on the exam? Since this quarter is redesigning those assignments a bit, I'm a little bit less sure of when assignments are, what assignments contain, when they're due, and how that relates to the exam. So if there's absolutely nothing on the assignment that would reasonably be on the exam, then I'll be lenient with the assignment because focus should be on the exam. So, information on that to come. I think that's just about it. We have a project due in 2 weeks. I haven't had anyone in my office talk to me about the project. I don't know what that means, but if you are someone who has not started the project, I highly recommend starting the project. It's not something that you can get done super quickly, usually. It's going to take a little while. Last time we introduced the context-free pumping lemma as an extension of the regular pumping lemma. So to recap that, we have infinite context-free language. We said there is an integer m representing the number of productions in a grammar with a limited number of terminals allowed per production, so that we could have a maximum number of productions that can be reached in order to create a string of that approximate length, that exact length. So just like with states in a DFA, this now means that for a string of a grammar of that many productions, we can now guarantee that strings can be made in some number of repetitions of those productions. So we choose a string that is long enough that we guarantee that we go through such a recursive procedure, which means that we can pump it, just like before. Our rules were the length of vxy, which is the length of the recursion, and the length of getting from the recursion to termination, that combination of a substring, has to be less than or equal to m characters. And the length of vy, that is the length of the recursion itself, is greater than or equal to 1. And so we can go from the start non-terminal to get to the recursion that produces u and z. That happens once. Then we go through the recursion that produces v and y, and we can go through that an arbitrary number of times. Then we go from the recursion to termination, and that produces x recursed in the middle of the string. So at the end of that, we have the string uvxyz. That is the original string that we picked. It's long enough to have to have gone through some recursion. So we call that recursion v and y. It could be multiple recursions, but we just pick one of them to be vy. And then we can pump it. Just like we did before, we end up with the string uv to the I, xy to the I, z, where I is the number of repetitions of that recursion that we did. And if uvxyz is in the language, then all uv to the I, xy to the I, z for all I from 0 through positive infinity, that you can't go through positive infinity, but up to positive infinity, have to also be in the language by definition. So we are looking for contradictions, just like we did before, where regardless of how vxy is picked, given those conditions up above, we have to be able to say regardless of how vxy was picked. So where in the string, we said it could be any sliding window of length m. It's not docked to the left like it was in the regular pumping lemma. But any way else, if we go back to the game, player 1 could pick vxy, we need to make sure that there exists some counterexample for some value of I. So we used the visualizer of a derivation tree to see this, to get a sense of what u and z were, what v and y were, what x was. Just a part of the string that is produced in the front and the rear for each of that. That's kind of where we ended. Has anyone slept on this and thought of some questions about how this works? We'll just need some practice. All right, if we're phrasing this like the game from before, as the other way that I like to think about the game, then we just want to be able to prove that player one cannot win the game. There is such a strategy for player two that player one cannot win the game. So to recap, it's exactly the same game as before, with the exact same turn order and turns, with the exception of the rules of what player one and player two are allowed to do are slightly different. Player one picks M. Player two picks a string with at least length M. This is exactly as true as before. But now player one, instead of choosing XY, chooses VXY, consistent with the constraint that the length of that has to be less than or equal to M, the value on their first turn. And then player two, which uses a value of I, such that UV to the I, XY to the IZ is not in L. And that can be a function of their breakdown of things like the length of VY of the pump. Just like we saw in a couple of our homework problems, it doesn't have to be a consistent I. It can be a function of I, such that regardless of what they pick for VXY, we need to be aware of everything that they could pick for that, and make sure that we always have an example of I that breaks that idea. So the way that I've been explaining this a little bit, that I've hesitated away from in class because it doesn't go so well, but I'll throw it on the board because I was reminded of it yesterday. And you can't see this in too many ways. I think I mentioned this once very early on, but it's very much like discretes. Player two is always giving an example. Player one is always has the options. So from player two's perspective, we need to say, regardless of what player one could do, here is the strategy that player two picks. So from discrete, when player one picks M, from player two's perspective, our argument has to consist of, for all possible M, we pick the string, there exists a W, such that player one chooses the decomposition of VXY for all possible VXY. And we can really just call it the length of VXY, but it's also the distribution of V and Y within each of those lengths. So we can't really just handle the length of Y like we did before, but this is all VXY breakdowns. Then there exists an I such that we find something that is not an L, such that UV to the I, X, Y to the I, Z is not an L. So this is the discrete way of thinking of this proof type, but this shows why it's difficult. Is that in terms of predicate logic, this is a highly nested statement, which means that we end up with a lot of work to do to come up with a process that works for all M for all VXY.
I feel like in some ways that's a little bit easier to understand because it's a lot higher. It's more specific and to the point, I guess.
Yeah. Yeah. If you have the background, it can make a lot of sense. It gives you a very easy path through exactly what's happening and what needs to be done. Phrasing it kind of like a game, all of the for alls are player one. We are just as player two are identifying the cases that work for each of these for alls. So if this helps, great. If it doesn't, feel free to forget that I said it. All right, time for an example. let's go through this. So just like we kind of started with the regular pumping lemma with a to the n, b to the n as a reasonably easy example to see, we're going to start with a to the n, b to the n, c to the n. So let's start with some intuition about why this isn't context-free. Imagine drawing an NPDA for this, or writing a context-free grammar for this. What roadblock do you hit when you're doing this? Yeah.
Well, you can load up, like if it was like A to the N, B to the N, you could load up the stack on the A's and load the stack on the B's.
Yep.
But for this, you would have to load it on the A's and then on the B's, B load, and then you'd have to load it again, and then you'd have to get to the end from there, the full stack.
Yeah. How do we know how full the stack was when it was as full as it could have been when we read the A's? We need to save that state somehow so that we can map it when we read the C's. And there's no additional storage aside from the stack, and there's no way within the confines of the stack to store how full the stack was. If we had one more integer worth of memory, we could do this. But we don't have that. So it's not context-free. From a context-free grammar, how did we do this with something like a to the n, b to the n? We recursed in the middle so that we made pairs of A's and B's. But how do we force the same amount of recursion in the middle of A's and B's and C's? We need 2 places, 2 points of recursion in the middle of that. And there's no way to guarantee that we go through the same amount of recursion once we move past that down into the recursion. There's no way to guarantee that these 2 threads are doing the same amount of work. They work independently from each other at that point. So either way that this makes intuitive sense, you're welcome to think of it from a grammar perspective, from a NPDA stack increasing and decreasing perspective. With that said, what's a good string to pick if we wanted to go through the pumping lemma to show that this is not context-free? Thoughts on what might work? Yeah.
We try to A to the N, B to the N, C to the N.
Sure. Sounds like a good idea. What makes you say that?
Just from the other component.
Yeah. Sometimes intuition, there's a pattern there, even if we don't necessarily know why that pattern exists or works. We know the string is of length at least m. There's no reason to overcomplicate it at this point. We want sliding windows of length m to minimize the number of cases. So even though something like a to the m over 2, b to the m over 2, c to the m over 2 is a string with length greater than or equal to m, how many overlapping sets of characters are there in sliding windows of length m? Here, sliding window of length m could give us all A's, could give us some A's and B's, all B's, some B's and C's, and all C's. If we did something like m over 2, we'd have to consider an additional case, some A's, some B's, some C's. That's unnecessary extra work that we shouldn't have to do. But it's also worth noting that no matter if we make this larger, a to the 10m, b to the 10m, c to the 10m, it doesn't remove any cases. Sliding window of length m has exactly those same cases. All A's and B's, all B's, B's and C's, all C's. So larger than m here does nothing for us. Smaller than m actually makes the problem hard, even if we can make a case that it's a valid string that we could pick. So in general, pick a string that's going to minimize the number of cases that your eventual proof will contain while still adhering to the constraints. Player one, that first for all, picks, the second for all, picks VXY to contain only A's, mix of A's and B's, only B's, mix of B's and C's, or only C's. There's no sliding window that will contain A's, B's, and C's, since there are M B's. There's no way to get NA and AC in that sliding window. So those are going to become our cases. And they're going to break down into further cases when we look at the possibilities for VXY. So context-free pumping lemma very frequently has lots of cases, but frequently those cases can either be combined or thought of in a similar way that allows us to shorthand things at least a little bit. So we know that once we get to this point, we need VXY to be less than or equal to M. That's that point. So we know those are the cases. We do know at this point that any I greater than or equal to 1 is going to produce a string not in the language. So that's the intuition. I'm going to break it down into those cases so we can see why. But this is one of those cases where you don't have to hunt for the correct I. Any value of I will work to break this pattern. So if we pick if player one picks all A's, one of the options that they have, that means there are some A's, some B's, some C's, and VXY, the recursion and termination, all happens within the A's. If that's the case, what happens to the string? We know the length of VY is at least 1. So it doesn't matter where it's coming from. We know that it's all A's. So if we set I to 2, how many characters are we adding to the string? How many A's are we adding to the string? Potentially.
Well, if it's, yeah. Really?
Somewhere between 2 is one of the options. It's all possibilities of the length of VY. Whatever the length of that recursion is. So let's say we have a string with, I don't know, 4 A's. Possibilities for VXY is that this is V, X and Y are both empty. This is V, this is X. This is V, this is X. This is V, this is X. Those are all the possibilities for Y being empty. V could be something. Let's see, we have V with an empty X, and that's Y. We could have, there are tons of combinations that are possible in here. And what we care about extracting from this is the length of VY. Because when we pump this an extra time, that's how many extra A's are going to be added to this string. So the length of VY has to be at least 1 in order for the recursion to add a terminal to the string, and it's capped at M, the size of this sliding window. It doesn't matter how the VY is broken up. If the length of V is 0, the length of Y is 4, the length of V is 2, the length of Y is 2, any other combination that allows for the sum of those to be 4. Doesn't matter, but the cap to this, the bounds are between 1 and 4. So greater than or equal to 1, less than or equal to M, the number of characters of A's that are in the string that we picked. So when we set I to 2, whatever this breakdown of VXY was, the length of VY is going to be the number of A's that we add to the resulting string when I equals 2. The new string is A to the M plus the length of VY, B to the M, C to the M, which since the length of VY has to be greater than or equal to 1, we know that there are more A's than there are B's. So the number of A's in we'll call this, I guess, LU prime is greater than the number of B's W prime, which cannot be a member of the language. Whenever that's true, we break the confines of what we picked. So that's the all A's case, and you can duplicate this logic for the all B's case and the all C's case. It's just a matter of where this plus the length of Vy goes in this, but regardless, we need the same number of A's and B's and C's. We pump only A's, only B's, or only C's. We end up with more of some character, the character that we pumped, than every other character. However, what happens when there's overlap? Overlap creates something that's a little bit interesting here. So if we know there are some A's and some B's, what does that mean? What are the possibilities for B and Y?
Is it possible to have A and A still as B and Y? Or is that
To have,
covered in
but
the last case? A and A, B and Y. If
yeah, that would be covered in the last case, because we have to have some A's and some B's. It implies there's at least one A and at least one B somewhere in BXY, in order for there to be that overlap.
So here it'd be A, B.
Yeah, there'd be some string of A's and B's somewhere in that. How could that possibly break down into further cases? Because you can imagine that we have a couple of A's and a couple of B's. It could be that V is empty, X is AAB, and Y is B. If this is X, this is Y, and B is empty, then this becomes the all B's case, because Vy is all B's. So it is absolutely possible to break this down into the other cases for some possible selections of VXY. Does that make sense? So if we were to look at what Vy is, it's just the string Y. And that's contained in the case Vxy is all B. It's contained in the case Vxy is all B's. It's exactly the same as if Vxy was all B's. When we pump this, we're just adding B's to the string. So it's the equivalent result of this. We care about the characters that V and Y contain, not the characters that X contain as much. So some options here break down into those first three cases. But there are some other cases that do not. If V and Y are both non-empty, then we know that there's at least one A and one B in the A's and B's case. So if X is something else and B is here, then what's our argument? What should we set I to, and why doesn't this work?
We'll consider it to anything.
Yeah. What's your condition for proving that it's not in the language?
Well, you would say, well, you would add something to the length of A and B. And because that length is greater than length C.
Yes. Yep. So now we're comparing A's and or B's to C's. Since we're not adding anything to C's, and there's no way this window can hit C's, we're doing something to A's and B's, but not to C's. So that becomes how you're going to target the fact that this case cannot be done. So it can either break down into one of the three cases that we already talked about, or it can be done in a way that creates imbalance between the A's and or B's and C's. And this case is also mirrored in the B's and C's. You're just doing something to the B's and C's that you aren't doing to the A's. So lots of cases. Some of those cases break down into further cases, but the breakdown of further cases are cases you've already covered. And then there are a lot of mirrored cases. So really the only logic that we need to write is for two cases. The all of one character and a mix of two characters. That's really the only templates that we need to make. And then we just need to make an argument that regardless of the breakdown of VXY, you're in one of those templates. So that is how I would approach this. Does that make sense to people, how this breaks down into cases that become other cases of templates? Let's draw it out kind of like a tree, I guess. So cases are so here we have, we're gonna call template 1. Here we're gonna have template 2. And the template 2, each of these is gonna break down into some cases that are template 1. So these are straightforward proofs. This is gonna break into some that's template 1 and some extra work that we're gonna call, I don't know what we're gonna call this. Rest. And this breaks down as well into some cases that are in template 1 and the rest. So the work that you need to do is to make a template 1 that shows how to prove when we're pumping only one character that you produce more of that character than the others. And then template 2, you're going to show that there are 2 possible breakdowns from here, one of which is a copy of template 1 if V or Y is empty. And the other is what happens if they're non-empty, and then you need to come up with the argument for why you have more A's and B's than C's, or more B's and C's than A's.
And the condition for VY is it must be greater than or equal to 1?
Yep. So we know if you set I to 2, we're adding at least 1 character. There's no way to not add any characters, which would be the only way that we could not show this. Thoughts on this, questions on this? Anything I can cover in more detail with regards to this example? Do you feel like you could write this out if you were tasked with this for homework?
Are we proving each case or is this arbitrary?
You are proving each of these cases, but you're proving them with the template. So you're not copying the same work over and over and over. It's the same thing like copying and pasting code. If you do that, there's something better that you can do. You can create a method that does that and then call a method in multiple places. So you're going to create 2 templates, and then for each case, you're going to say which template applies and why. And that way, it's not so much work that this could be an entire week's assignment. Yes.
So if you're trying to build a string for W prime, with like A's and B's, for example.
Yeah.
How would you build that string so that you could show like algebraically what you meant of it? Because when we were doing the other ones with the regular grams, you could like literally work through the string and add stuff together, and then you would get a result that you could show it not in the language always.
Yeah.
But this seems like more of an argument from intuition.
It is definitely more of an argument from intuition for the moment. And the way you would turn this mathematical is you're going to look at just the length of Vy. This could actually break down into further cases if we wanted to overcomplicate it. Like, what if V is some A's and some B's? When we duplicate this, now we're not in the order of the language anymore. That would work. But mathematically or algebraically, what we care about is the length of Vy. I don't think that's quite what you asked.
That's satisfying.
When you duplicate the length of Vy algebraically, you're going to, when you break it down into UVXYZ, you're going to be showing the parts of that are coming from particular parts of the string. So you can start making claims about the length of that. So when we have UV to the I, X, Y to the I, Z, if we're in the case, for instance, that this is for A's, then we know all of this comes from the A's, and Z handles the remaining A's, potentially, and all of the B's and all of the C's. So since we have all of this duplication here, the extra duplication has to come from that, which feeds right back into the a to the m plus the length of vy. When you set I equal to 2, you're duplicating the v and the y. So that's why, since we know these are coming from all a's, this is how much extra a we are adding. Yeah, this would basically be your template for template 1, is you say that for some character, call that character something else. When vxy is contained all of that character, then we know that this portion of the string is all that character. All the duplication is coming from that character. And so we end up with that character to the m plus the length of vy when we've set I equal to 2. And then when you look at case 1, all a's, you say substitute that character for a. And you look at case 2, all b's, substitute the character in template 1 for b. It's like a parameter and a method. We're creating the method with a variable, whatever character is contained with vxy. And then we call that method within our template whenever we're making the cases for each of those. We just say, here is the template, here is the instantiating variable. It's the a in this case. It's the b in this case. So it's exactly like what is saved by writing a method, calling a method, instantiating a temporary variable in that method with something from another scope. I don't know if I've explained it that way before, but I really like it.
So if we have a B for template 2 in the case of the rest, it would be that a n plus the length of y. For B, it would be also n plus the length of y.
Yes, the b, yeah. Well, if you're saying you're calling it for the a's and b's case,
For under template 2, for the a's and b's in the rest case.
yeah, you don't necessarily have the length of vy. It's split between a's and a's and b's, but you know you're adding the length of vy, a's and b's, which has to be at least 1, which means that either the a's or the b's or both combined have more than the c's. Not both combined, but the average of a's and b's, which means that there has to be some value of a's or b's that is greater than c's. Yeah.
Could you write like a W prime for like a to the n plus the number of a's in vy, and then b to the n plus the number of b's in vy, and that's going to give you the a's and b's?
You could. That would be based on the exact breakdown. And you know that at least one of those has to be 1 or more. So that says that either the a's or the b's are greater than c's, and that will work.
Could you say, because we know the a's are before the b's, that would be a to the n plus length of v?
We don't know that v consists of all a's. It could be that v is AAB.
Right, but for the case where it's has to be in that form.
Right. You could either break this down into more cases. One of the cases is that v is all a's, y is all b's, but it ends up being unnecessary if you just look at the number of a's and b's compared to c's.
Okay.
I think that would be, it's a good way of thinking of it, but it creates unnecessary work for you when you're breaking down into further cases. Bring those up in a way that a single logical case covers every possible breakdown. That ends up making your life a lot easier when possible. But that is again a very good thing to note, that there are possible ways that we could break this down where b's are all a's, y's are all b's, b's are a's and b's, y's are all b's, b's are all a's, y's are a's and b's. B is empty, y is empty. Lots of further complications that are possible when we think of this. So this is where thinking about the cases before you dive into the proof can make a problem that is potentially very long much shorter. Other questions? How are we doing with this? I get it, but I think I'm going to change my mind soon.
That's how I read that.
All right, so this is an example of that. Let's look at another. The language WW is not context free. This is interesting because WWR was context free. So what changes between WWR and WW that makes WW not context free? Anyone think of that intuition as to why that is? That might help us in this proof. Yeah.
Because WWR is a palindrome, so you can just add the two pairs in the middle, whereas this one you can't.
Yeah, so when we're looking at this like a stack, you fill the stack and then empty the stack, and you empty the stack in the reverse order of the string that you read in. WW, you need to read the string and then read the string again. What data structure does that make you think of?
A queue.
A queue. If we could read this in with a queue instead of a stack, then we could parse W and then go back to the front of the queue and parse W again. But we don't have a queue moving along with us. We have a stack moving along with us. So because of that, this isn't going to be context free.
Or I guess couldn't it also work if we knew the length of the string beforehand?
We need a second stack to be able to do that, I feel like. If we had a second stack, a queue can be emulated with two stacks, but you would fill up the stack, remove everything except the last character, put that in the other stack, check that character. Then the next character you need to check it on the top of that stack. But then the next thing is on the bottom, so you have to go back and forth between the two stacks to keep accessing the front character. To further show this, let's think about a good string to pick. Any thoughts on a good string to pick? Yeah.
Could we do like A to the M, A to the N? Like that?
A to the M, A to the M. Interesting. So there needs to be an even number of A's in the string. I would argue that's probably regular, and that we could have two states that go between acceptance, rejection, acceptance, rejection, acceptance, rejection, and the DFA.
But it would also be an element of that.
It would be an element of that.
Something else. Nice.
To A to the M, B to the M, A to the M, B to the M. So that.
Yeah, repeating A to the M, B to the M multiple times. So we know we can handle A to the M, B to the M in a context-free language, but what if we duplicated it? When we fill up a stack of A's, we can map those to the number of B's, but when we get to the second A to the M, B to the M, how do we know that there were the same number of A's and B's as the first time? Because the stack is now empty. We've lost a handle on what M was. We need to map M to M in the first half to the second half. So I like that a lot. It's a really good pick. Does it make sense why when we have a stack here, this is a string that we couldn't handle with a stack? We can handle the first half, but when we get to the second half, there's no way to verify that M equals M. So back to player one. They can pick the breakdown of VXY, the cases, all A's, some A's and some B's, all B's, or some B's followed by A's. So now the order matters a bit. Maybe you can create some templates though that break down into those cases. How would we handle the breakdown for each of these cases? There's no C's to attach to. So when you have overlaps of A's and B's now, there's no, well, there's more A's or B's than there are C's that we can attach ourselves to. So how could we handle this? Take a few minutes and think about that, talk about it in small groups.
Yeah, so number of A plus number of B's is all things all. Things add up to length one. So then I just put slide up into two. So, okay, add A first, second. And then either way, one of these has to be greater than or equal to one. Which means that they would not both equal should have. I do. I do that. If I could do that. And then the views fall by eight. So that I have these plans. And you that. Right. Yeah, some makes it look. Actually, it's just up there.
So for this string to adhere to WW, what are some conditions that have to be true about this string or any modifications we make to this string? Do note that the resulting string doesn't have to be the same as A to the M, B to the M, A to the M, B to the M anymore. If we make changes to something like these A's, it's still in WW if we make the equivalent changes to these A's. So I think we can identify that the number of these A's need to stay consistent with the number of those A's. And the number of these B's need to stay consistent with the number of these B's. So any change we make has to be mirrored on the other half of this. But since we chose M for each of these, there's no way for a sliding window of length M to reach the other side of that. There are MBs in between these A's and these A's. There are MAs between these B's and these B's. So even when we break this down into cases, we're going to be making a change to one or the other of these, and it's not going to be mirrored in the other half of this string. That's the intuitive approach to this. But we still need to break it down into cases to show that no matter what we do, that will always be true. So there were those cases, but I think will be good practice between today and tomorrow being Monday, in addition to an assignment and preparing for an exam, etc., is to think about why this works for each of those cases. I don't think we have time to fully show this before the end of class. So what I should probably do with the last couple of minutes that we have is ask if there are any questions on the intuition of that breakdown so that you can give it a shot between now and Monday, so that you can apply this idea to the homework that may or may not get pushed back depending on if there's exam relevant material on it. Any questions? That make sense?
We'll have two templates for this question, right?
Yeah. It becomes a little bit tricky when you're looking at the cases of A's versus B's and B's versus A's. Because if we're targeting the B's and the A's in the middle, then we're making some changes, but we can see that the changes that we're making can't affect these A's and these B's. So every change still has to be mirrored when we're looking at the first half of the string and the second half of the string, the second half of the string and the first half of the string. And I think that that approach makes it easy to make arguments for each of those cases. But yeah, I would have two templates, one for each of the individual characters and one for overlaps. All right, I'm gonna go start some office hours. Feel free to swing by.
Awesome.